Good afternoon.
Good afternoon.
So thank you for being here. So my name is Samir. I'm an AI ML solutions architect at AWS, and I'm here with my colleague Max.
Max Liu, also from AWS. I'm the principal specialist for accelerated computing.
So we know that the size of the machine learning models is growing fast year over year. And if you take a look back at 2 or 3 years ago, the model sizes were about hundreds of thousands of parameters or even a few millions of parameters. But now we're talking about 20 billion parameters, 30 billion parameters, and eventually in the near future we'll talk about trillions of parameters. If you're not familiar with this term parameter, you can understand this like a number. Floating point numbers are an integer number represented by a data type inside the model, the training model. So weights learned during training are basically represented as a parameter inside the model. And if you have like many parameters, you're talking about, let's say, billions of parameters, you're talking about a very big model, right? And, but on the other hand, the technology is also evolving for building more efficient GPUs, accelerators for you to train and to run your machine learning models, and CPUs as well. But this also adds a complexity in the life of the data scientists, right? So you have lots of devices, lots of accelerators. You need to choose which one is the best option for you. So this is what this session is about. So we're going to show you a few offerings of AWS, so in terms of GPUs, hardware, accelerators, CPUs, but also we'll try to provide some guidelines for you, for machine learning specialists, to select the best combination of these hardware elements, okay? If we take a look at the potential machine learning workloads, we can try to classify them into these 3 scenarios. So small, intermediate, big and huge. So for this small scenario, you can understand like simple or classic machine learning models trained using small data sets or toy data sets, and then you can just run on your laptop, right? So you don't need like big instances to run these workloads. And we're not to cover this scenario in this session. Let's instead focus on the other 2. So intermediate big models is the most common scenario. For most of the customers are trying to implement solutions using these type of models, this size of models. And also and to train a model, an intermediate size model, you also need some data, not a lot of data, but we can talk about like 500 gigabytes of data. It's an intermediate size data set for you to train your models. And then you have the huge models. And then we are, in this scenario, we're talking about models with billions of parameters. And these gigantic models, they are data hungry. And then you need to have like terabytes, eventually petabytes of data to train these models. And this is a very extreme scenario. Not all customers are running workloads in this scenario, but this is something that we're going to talk about here. Okay, so in the data scientist or the machine learning developer's perspective, you are trying to focus on the use case, the challenge, to find the best model, to prepare your data set. And in the end, you just need to build or to deploy your model, right? But with so many options, you need to consider these options in order to achieve maximum performance and also reduce cost of your workload. And this is one of the biggest challenges for the data scientists, right? So many options, so many possibilities, and which one is the best one for your scenario? So, and then you have some common questions that may be asked. So, shall I use CPU or I need like an accelerator, a GPU or a dedicated accelerator to train my model? Also, do I need distributed training to train my model, or I can use one single accelerator, one single instance to do that? So which file system should I use to store my data set in order to have good performance when the data set is being streamed to the host that will train these models? And also, when you define, when you are running distributed training, you need to have like a very good network to transfer not only the data set, but also to synchronize the models and the gradients across multiple instances. And this is also an important point that you need to be careful, right? And one last thing, and this is related to the third scenario, the huge models, when we talk about billions of parameters, there's a spoiler there. So with the spoiler is, when you have a situation like this, you need a supercomputer. And then the direct answer is the Amazon EC2 UltraCluster. So an UltraCluster, Max will cover these more in the next slides, but basically an UltraCluster is a supercomputer inside your AWS account. So, and by supercomputer, I mean, if you take a look at the number 1 or 2 supercomputers in the top 500 supercomputers, you can see that you can launch something even bigger than the ones in that list. Okay, so Max, could you talk a little bit about the AWS offerings?
Yeah, absolutely. Thanks, Amir. So, you know, we're here to help you. At AWS, we innovate on your behalf, our dear customers. And we have built the broadest and most complete set of machine learning capabilities for builders of all levels of expertise. If you are a business analyst or apps developer with limited machine learning skills, you can still build intelligence in your applications by using AWS's managed AI services. Well, if you're a data scientist who wants to build, fine-tune, and eventually deploy your model at a large scale, but in the same time, you don't really want to manage the infrastructure, then you can use our managed services called SageMaker with the end-to-end capabilities to help you on that regard. In the same time, manages the infrastructure on your behalf. Of course, if you are this type of expert practitioners who wants to make sure that you have the exact infrastructure choice you want, and you want to build the most optimal combination of that, we're here to help as well. Actually, at AWS, we also have the broadest and deepest infrastructure for AI machine learning. If you look at the portfolio we have multiple instances powered by CPUs from Intel and AMD, by the GPUs from NVIDIA and AMD, and also the custom accelerators from either AWS's Annapurna Labs and also our partner Intel Habana Lab. Now, we have grouped these instances into 3 categories. If your focus area is around building the traditional machine learning models, training them, doing inference, then perhaps you should look into the CPU-enabled instances. On the other side of the spectrum, if you're building very large, for example, language models for training purposes, then you should consider the P-family instances powered by the latest and greatest NVIDIA GPUs, A100 and B100. Also, the DL1 instance powered by Habana Labs Gaudi chips. And of course, TRN1 instance by our own AWS Trainium chips. So, as you can see, these are 2 ends of the spectrum. But if your need is really in the middle, from a performance perspective, but in the same time, you want to see large-scale deployment in terms of machine learning training, inference, then there are multiple options you have, and there are multiple factors you need to consider. Apparently, you want to make sure you have good performance, typically measured by throughput and latency. You need to focus on cost, right? You want to make sure it is cost efficient. But also, you want to take care of your engineering teams. You want to make sure their productivity is high, the instances you choose are easy to use, and have a very broad support of the models and the frameworks. So here, we kind of created a cheat sheet for you by laying out the key factors you ought to consider and put them against different categories of instances. Again, here your preference matters. If your priority is around having very fast experiments across multiple different models, you want to have flexibility, you want to make sure that your engineers spend least time to learn about the instance, but spend most time trying to build the models themselves, then you perhaps want to use the CPUs to get started. But now, when you start to grow the workload, want to grow your business, want to have a bigger size deployment, then you should start to migrate into the GPUs, especially the GPUs from our G family instances powered by NVIDIA GPUs. They're more performant, they have a very broad model support, and typically support very popular frameworks like PyTorch and TensorFlow. Now, good news, your business has grown so much that you need to deploy to a very large deployment base, and you want to run the production on a daily basis with a lot of inference that you want to do. Then here, you really need to push up to the best performance you can get, lowest latency you can get, of course, lowest cost. And when you're facing a situation like this, we recommend you to consider using AWS Inferentia, and it's powered the Inf1 instances. So Inferentia is the first generation of machine learning custom chip that we built, specialized on deep learning inference. It offers high performance at a very competitive low price point. In the past couple of years, we've made a lot of improvements in terms of broadening its model support and integrating its SDK into the most popular frameworks like PyTorch and TensorFlow. And also, we start to see a growing ecosystem from our partners and also the developer community. We're here to help you to work through that learning curve. Of course, our innovation around driving faster and better machine learning acceleration doesn't stop at Inferentia. We actually also start looking to the GPU domain and want to make sure that our GPU offerings powered by Graviton chips also have better and better machine learning capabilities. So Samir, do you want to talk about our innovation around that for Graviton 3?
Sure. So we can start talking about the machine learning workloads that are more appropriate for CPUs. So when you have classic machine learning models or you're using frameworks like scikit-learn, they were created for CPUs. And so it makes sense for you to just use CPUs. And if you manage to use a better CPU or a cheaper CPU and achieve the same performance, this is the best scenario. So Max talked a little bit about the silicon technology that we created. So for Inferentia, for Trainium, and Graviton is another technology that we created internally. Graviton is an ARM 64-bit CPU created from ground up by AWS for general purpose. But more specifically, this CPU, it brings some accelerators, so SIND accelerators. So these accelerators, they are kind of small GPUs inside the CPU. You can execute vectorized operations in just one cycle of the CPU instead of having to sequentially apply all these operations. And this is very important for machine learning models. It accelerates a lot your model. And also, it brings the support for BF16, which is a new data type that reduces the size of the model and keeps improving the performance of the execution of the model, but with a minimal impact on the performance in accuracy and so on. So just to give an idea in terms of the evolution of the platform, this is a comparison between Graviton V2 and V3. So C6G is a Graviton V2 instance, and a C7G is a Graviton V3. The machine learning model that we use to compare is a BERT, which is an NLP model, a natural language processing model used to answer questions. And as you can see here, so with the use of the SIND coprocessors and the BF16 present in Graviton V3, so a C7G managed to achieve 2.5 times more performance than Graviton V2 which is very good for most of the models. And as you can see here, this is not only classic machine learning models that we're talking about. The evolution of the CPUs is allowing us to run deep learning models as well and bigger models. So it's important to experiment a little bit with the CPUs also before transitioning to GPUs, right, in terms of thinking about the cost of your workloads. So now it's time to talk about the accelerators.
All right, awesome. See, now if your focus point want to put on larger models, right, and you want to train them not only on a single machine, sometimes on multiple machines in a cluster, this is the time when you need to look into the accelerated computing options. Here we have a list of different families that we have to offer, ranging from TRN1. This is, as I said before, powered by Trainium chips. There's a P family, the G family, and also the DL1 instances. Regardless of the specific instance types, if you take a step back and look at the architecture of the server, they always come with two types of components for compute. One is the CPU host, right, that manages the server and also has access to the system memory, and also the accelerator with its own accelerator memory. So if you look into the types of tasks for these two compute components, CPUs are very good at doing sequential computation. And as Samir said, with the recent development of the CMD instruction sets, they're also getting very good at vectorized compute. On the other hand, from the accelerator side, they are very good at parallel operations, especially for matrix to matrix and matrix to vector multiplication and accumulate. So as you pick up one instance, right, when you read through them, usually you're going to see a very long spec sheet. You're going to see a lot of documentation. Sometimes it could be overwhelming, right? Where do I look at to make sure that this instance type is good for me, good for my workload, for my use case? Let's use one example to show you how to go through that process and where to look at it. Here, this example is from our most recently launched TRN1 instances. As I said earlier, it is powered by AWS Trainium, and we've done a lot of innovation to make sure it has very high performance at a very low price point for deep learning model training. It offers good performance, right? If you look at the half precision performance, it goes as high as 3.4 petaflops for one Trainium instance. And that is 40% higher than the most recent, the latest GPU-powered instances, P4D. And actually, the single precision performance is 5 times higher at 840 teraflops of speed. And this is very important for those of you who need to run scientific workloads where higher precision matters. Also, we equipped this device with high-speed memory with up to 512 gigabytes per instance and 13.1 terabytes per second of a bandwidth. From a networking perspective, it comes with 800 gigabit per second for EFA. And this is by far the fastest EC2 instance with a EFA at this speed. But we're not stopping there. We're actually working on the next iteration of TRN1. We call it TRN1N, with twice of the networking speed at up to 1,600 gigabit per second. We're going to talk more about TRN1N in the coming month. So for those of you who are familiar with large-scale training, especially when it comes to distributed training, you know that collective communications ops, we call them connective ops for short, is very important, right? The more efficient, the faster you can run those collective ops, the faster you can train across multiple machines within a cluster. And we've done a lot of innovation to improve on the performance of collective ops. Within the chip, there are two types of compute engines. Actually, there's one called communication engines to separate from the actual compute engines with doing the actual compute work. So your communication tasks and computation tasks are running in parallel. And this helps to improve the speed and convergence of your training through collective ops. And outside of the chip, between two chips, we have the high bandwidth, low latency interconnect that we call neural links. And between the servers, we have the EFAs. It is very important to note that these two layers of interconnect are independent, which means we can move data fast on these two interconnects without any interference, which means, again, faster collective ops and faster training. And that's within the server and across servers. Now, at the data center level, we're also making additional improvement. And this goes back to the UltraCluster notion that Samir said earlier. We have this concept built for our previous generation of GPU-based instances, and they're now getting better with TRN1 because of primarily two things. Number one, we have much faster networking, and number two, the Trainium chips that we put into the servers and data centers are very power efficient. And these enabled us to build even bigger UltraClusters by putting more accelerators into those big data centers. We can actually put more than 30,000 chips into one UltraCluster. And that adds up to 6 exaflops of a compute. That's indeed the supercompute capability on demand. So you can build your own, use your own UltraCluster and scale up and down based on your need on demand. Now, with all these capabilities, how does TRN1 perform? So we've run a few benchmarking tests using the BERT large model and compared TRN1 here in green against P4D in red. And we've run these tests on a single node or on up to 16 instances node. And here you can see that with TRN1, we achieved up to 1.6x better performance than the latest GPU instance P4D. And that comes with more than 50% of the cost saving per training. All right, we've talked a lot about TRN1 as an example to show you how do you go through the selection process and where to focus on in terms of the specs and also the features. Let's take a step back and see what are the other things we need to pay attention to when it comes to large-scale distributed training. Samir?
So now let's talk about distributed training. But before we jump into the different modes or different ways of running distributed training, why do you need distributed training at all? So if you have like a huge model, a model that doesn't fit into your accelerator memory, so let's suppose you have one GPU or one training accelerator, and the model is too big for that accelerator. So you need to slice this model and use multiple accelerators, multiple GPUs, and then you load these slices across these multiple accelerators. This is one reason for you to run distributed training. If you have just one instance with multiple GPUs or multiple accelerators, you can run distributed training inside just one instance. But if your model is too big even for that instance, you can load or launch multiple instances and then slice your model and load across all the accelerators across all the nodes. And this is another reason or another way to run distributed training. Another reason for you to run distributed training is if you want to run faster. So you have a big data set, you can slice this data set send portions or batches of this data set to different nodes, and then you run your training faster. So these are basically the two reasons, and also you can combine both, right? So you have a big model, but you want to train it faster. So there are different ways to run distributed training. I will show you three. This is the first one, so data parallelism is the simplest one. So you have a model that fits into the memory of your accelerator. And then, in this case, we have 4 workers. And these workers, basically, they represent the accelerators, can be spread across different instances or in the same instance, right? And then you load this, multiple copies of the same model across all these accelerators, slice your data set into mini batches, and send different batches to each one of these workers. The workers will train the models using that particular batch. And then after the first round finishes, it will basically share the gradients across a ring, and then the model will be merged. And then you have another copy that is then copied back to all the workers, and then you slice your data set again and repeat the process over and over again. But what if your model doesn't fit into the accelerator memory, right? Then you need to use a different strategy. There is another one called pipeline parallelism, where you slice your model using layers, using the layers of your models as references. So you load layers 1 and 2 into worker 1, layer 3 into worker 2, and layer 4 into worker 3, right? And then you create this notion of a pipeline. You slice your data set into multiple batches, but you pass your batches across this pipeline. So you don't distribute your batches, your data. You just use this pipeline. So as soon as the worker 1 finishes, it can start working in the next batch, and so on. And then each batch will start passing from one worker to another one. This addresses the problem of slicing a big model and a big data set, but the problem is idleness. So while the worker 1 is working, the other workers are idle, waiting for data. Even if you start sending multiple batches in parallel, some of these workers will suffer from idleness. So you're not using the GPUs or the accelerator at maximum capacity. And this is something that Trainium minimizes. So Max mentioned the collective engine is inside Trainium, the chip that we created to accelerate the training process. Different than a CUDA-based system. So a CUDA-based system is a GPU, an NVIDIA GPU. So it uses a CUDA driver to communicate with the GPU. It doesn't do communication and computation at the same time, the CUDA, but Trainium does because of the collective engines. So by decoupling these two things, you can minimize idleness in this mode. But yeah, and another thing is, what if your model, even slicing in layers, it will not fit into the workers or the accelerators. So you need to use a different strategy, which is tensor parallelism. Instead of slicing your model per layers, you slice per tensors. You select a few tensors and load only these tensors to each one of the workers, right? The rest of the process is similar to the pipeline parallelism. But this is another strategy that you can adopt if you're training a huge model, like the 20 billion parameters. And then we can connect these two things. So the UltraCluster with up to 33K accelerators and a huge model is slicing with using the tensors as the parameter and then loading this big model and training it faster in the UltraCluster. Okay? But how many, raise your hands if you never heard about SageMaker, please. So most of you are familiar with SageMaker. So just so I will not spend too much time on SageMaker, but I would like to highlight the importance of SageMaker. Because SageMaker is a service, or a managed service that was created by AWS to simplify the machine learning pipeline. So, and alleviate the effort of launching EC2 instances, launching the clusters, launching the operational systems, applying security patches, configuring the network, configuring the Docker manager and everything. So basically with SageMaker, you have an API. You have, the data scientist has access to many APIs through an SDK where you can just invoke these APIs and launch the service. So if you want to train a model using SageMaker and using Trainium, for instance, or using GPUs in multiple hosts, you basically invoke an API, passing some parameters, and then SageMaker will launch the instances, configure everything, start the training process, slice the data set, distribute it across the nodes, train your model, save to a S3, then destroy the infrastructure after the training. So you don't need to worry about the infrastructure. The same if you want to deploy the model. You just invoke another API, it gets your trained model, exposes as a web service, and then you can just integrate with your application and start invoking these models immediately. So, and then when you talk about distributed training on SageMaker, you also need to take to pay attention to the way you save your model and the way SageMaker will basically copy the model, the data set from S3 to the hosts. There are a few modes that you can use. If you're dealing with a small data set, let's say 100 gigabytes or less, you can use fast file mode or file mode. File mode will basically copy the whole data set from S3 to all the hosts that you launched. If you have a big data set, it will take a long time to kick off the training. So it's better to try and find the best threshold for the size of your data set. And fast file mode allows you to create like a virtual version of your data set inside the instances. Your data is not copied to the instance, but instead you can just read from this virtual interface, and then the data is streamed directly from S3 into the memory. So it allows you to kick off your training faster, and then you can stream the data. And the data can also be splitted on S3 and send only portions of this data to each one of your nodes. Right? This is the simplest way to kick off a training job using SageMaker, even using distributed training. But if you're storing your data into a network file system like EFS, so you can just provide the endpoint of EFS to SageMaker. It will mount the file system to all the instances of your training, and then your code can just read directly from EFS and train your model, right? But if you're talking about a huge model, a big data set, terabytes, petabytes of data, eventually you need like the maximum performance and a high throughput, lower latency in this process. And then you can use FSX for Lustry, which is another type of file system that is compatible with SageMaker. It's similar to EFS in terms of the way you mount. You just point SageMaker to the endpoint of FSX for Lustry, and then it will mount to the instance, and then you can read the data with maximum performance. And by the way, when you launch an UltraCluster with Trainium, this is the type of the file system that you use, right? Because it's necessary when you have like a huge data set. So now let me talk about a use case. This is a real use case. So I'm working with a customer that they make robots and have machines to automate manufacturing lines. And they sell this equipment to their customers. And eventually after a while, so these parts, they can break during the manufacturing. And their customers, basically, when a part is broken, they take a picture of this part and send to them, to say, hey, I need a replacement for this part. And today, the operator needs to search into a database of more than 50,000 parts based on that picture. Sometimes the picture is, the part is too much damaged, so it's hard to find any identification. So the operator needs to try to find this part, and it's a nightmare. So what we propose to them to create a visual search mechanism and using SageMaker and a few accelerators. A visual search mechanism is basically a way to search a database using images as input, right? And then they created a data set with parts, all of their parts with labels showing where in the picture the parts are, the types of the parts and everything. And then their data scientists basically worked to build two different models. One computer vision model to detect the parts in the picture sent by their customers, and another model, which is a clustering model, to find the similarities, so the distances between the parts. And in the end, create a list for the operator with just a few potential parts for them to select which one is the correct one. Okay? So in the end, we created we used SageMaker pipelines to create an automated pipeline that basically kicks off a SageMaker processing job at the beginning to generate synthetic data. So they have 3D models of all the 50,000 parts and with CAD files. And then they basically created a mechanism to run inside SageMaker processing jobs and using GPUs to render these parts using Blender. Blender is an open source 3D modeler. So basically Blender reads these models, render the parts in different angles with different backgrounds, and generates a synthetic data set. And then this data set is used to train the computer vision model, a YOLO v5 model. So, and basically they have around 500 gigabytes of images, a YOLO v5 model that is then used to do two things. First, it detects the model and returns a bounding box around the object in the picture. And then after identifying the part, so they are using the backbone or the structure behind the neural network to extract some features and create a vector of features. This vector basically identifies the features inside the image. And this vector is then sent to the clustering model, so the KNN. And based on these vectors, this model measures the distances between this vector and the other vectors, the other 50,000 vectors, and finds the most similar parts, and then it returns a list for the operator. So initially, and this whole process was very experimental when they started, and this training was taking days to complete. And after this first iteration with SageMaker and using G4 instances to run the processing job that generates the data set, they managed to reduce cost and time with this. This was an important step. And why G4 instances? Because Blender is a 3D renderer, so it uses OpenGL, which is a library that accelerates 3D rendering. And that's why they use G4 instances to accelerate this. Another two G4 instances to train YOLO v5, now they are experimenting Trainium to try to simplify this even more. Because now they are launching two different instances. With Trainium, they will be able to launch just one instance and you run distributed training using just one instance. And for the KNN is a classic machine learning. It runs on CPU. So a C5 instance was used to train this model, and they are also using the same C5 to run the model. They are also experimenting with Graviton as well to try to optimize this model. And finally, they are deploying these two models on SageMaker endpoints that expose these models as endpoints. And for the KNN, it's basically deployed on a C5-based instance, a CPU instance. And the YOLO v5 is being accelerated by an inferential chip. So the service that Max talked about. So with this chip, this is an alternative for the GPUs for you to run your model faster and with a lower cost, because the chip was created specifically for accelerating your machine learning model. So if you're curious about this, we can talk offline about how they implemented this in terms of the optimization of the images, how to send this to SageMaker, and how to create batches of images inside this endpoint to optimize even more the inference. Okay? So, Max, do you have any other interesting stories to talk about?
You bet. Actually, the case study that Samir talked about was definitely not unique because we've helped thousands of customers literally to go through a similar process and help them to find the right instance for their jobs. So here I have a few customer stories to share. The first one comes from Finch Computing. They're the company specialized around building NLP models to help their customers to uncover new insights from a huge amount of text-based data. And as you can imagine, as in their workload and use case requirements, they want to have very fast response time, so their customers don't need to wait. And they need to continue to add new language supports for their models. This is when they started to look at AWS Inferentia. So we worked with them and helped them to migrate their workloads to Inferentia. And through that course, they managed to see more than 80% of cost savings while maintaining the throughput and real-time response time requirements. And more importantly, the time to build new models and add new language support is very important for their business. With the help of Inferentia, they managed to add new languages. For example, a Ukrainian language to their model in just 2 days, so which is very fast from a time to production perspective. And they're continuing on that journey and migrating more models to Inferentia. I have another example from our internal customer. They're Amazon Robotics. You know, at Amazon, we operate a lot of fulfillment centers, hundreds of them, right? And in those fulfillment centers, the flow of inventory is a very important metric. For those of you who have already put down orders today is Cyber Monday, you would expect your order will come to your door very fast. And this is what we do within our fulfillment centers, trying to improve the speed of the flow of inventory. So in those fulfillment centers, there are 3 very important physical components to manage the flow of inventory. There are these units that we call the mobile shelving units, the robots, and also the employees' workstations. So the robots move the mobile shelving units to the stations, and then the employees will put in the inventory, we call them stowing action, or take out the inventory, the pickup action. So the robotics team built a deep learning-based CV system to train on top of millions of videos of the stowing action in order to improve the workflow. And as their workload grows, they face 2 challenges. Number 1, they want to scale their compute resources very efficiently. And number 2, they wanted to manage their infrastructure without spending too much time. Right? So with the help of SageMaker and Inferentia, they've achieved both goals together at the same time. They managed to reduce the cost for inference by up to 70%, and also improve the performance of the workflow by 40%. In the same time, they're able to do more inference per day. Now they're capable of scale up to 200 million inferences per day, which is a very big number given the size of operations we have. Now the last example I have here is from the life science industry. We have a customer called Page, and they build very advanced, very complex machine learning applications for precision diagnosis and treatment. Think about things like cancer detection and treatment. So before having their workflow in the cloud, they actually had a HPC cluster on premises. They use that HPC cluster to run their machine learning models and associated software. As their business grows, they face the problem again around scaling. And they decided to build a hybrid model by scaling their machine learning related resources in the cloud. By using AWS EC2 P4D instances, they managed to improve on their internal flows by 72%, in the same time with lowered cost. And also, very importantly, they freed up the time for their employees to focus on the innovation that they really care about, which is cancer detection and treatment. And we're happy that they work with AWS to drive that front end for this new era of cancer treatment and detection. All right, today we talk a lot about the key considerations you ought to have when you're trying to choose the right instance type for your machine learning training and inference jobs. To learn more about EC2 instances for accelerated computing and also AWS SageMaker, please feel free to scan the QR code on screen here. And again, we're Max and Samir. Thank you very much for you spending time today. And please make sure to complete the session survey in the mobile app so we can collect more data. We're a data-driven company, and we can continue to improve on the sessions. Thank you very much.